Okay guys, so we've talked about how to find the resultant of two vectors that are at right angles to each other. So just a brief recap, there's a couple of ways you can do it. Let's say that one's going that direction, one's going that direction. The first thing you can do is you can just join up, move this vector so it starts where this one ends. That's when we do it, like that, to make it into a triangle. So I've just moved this vector over here. So the tail end of this vector is beside the head of this one, and the resultant is that vector there. And you can calculate the angle using the sine rules and the trigonometric ratios, and you can calculate how long it is by using Pythagoras' theorem. So if that was 4, let's say, meters per second, because remember it's any vector, and let's say that was 6 meters per second, and I asked you to find out the direction, what's the angle here, and also how big it is, you could do that fairly easily. So first off, let's get the extent, the magnitude of it, how big the vector is. Well, it's the square of 4 plus the square of 6. So I got 52, and it's the square root of that. So for my answer, I got, and I'm just going to hold this up to the camera, I got 2 times root 13, okay? Now, I don't want you guys getting intimidated, that might sound patronizing. If you encounter surds like this, a lot of people, if you haven't practiced them in a while, it can freak people out. This just means the square root of this number, okay? And I want you to realize that is literally just a number. So for example, if I said like the square root of 16, you all know that that's 4. Right? That's just a number. That's all it is. So just because the calculator gives you this answer in square root time, don't be intimidated. It's still just a number with whatever units you're using. So this is 2 times root 13 meters per second. Now the reason the calculator does that is if you try to get the root of 13, you're going to get like a rounding error. It's going to approximate it. It'll be like 3.424, whatever, okay? So to try and keep things accurate, it leaves it as a square root for as long as possible. Now, if you want to get the actual numerical value, if you want to find out what that actual number is, remember you just press that SD button. And this is telling me that that number there is 7.21110251. But let's just go to 2 decimal places for this one for the sake of it. 7.21 meters per second. So you can use the Pythagoras theorem to figure out how big the vector is. And as for the angle, if we want to find out what the angle is, well, oops, that's 4, that was 6. But we're going to use one of our trigonometric ratios. So we're trying to find out what this angle here, we'll call it theta. So what do we know? Well, let's pretend we hadn't figured out this. And even if now we've calculated this, right? I'm still going to use these numbers just because they're nice round numbers. It's going to be easier to use rather than when we've calculated and approximated. So we're looking to try and find this angle here. So let's think of our ratios. We have, in fact, I've already got it pre-written for later use. We could use any one of these, sine, cos, cosine, or tan. We know the adjacent, we know the opposite, so I think tan is going to be our winner here. So the tan of this angle is equal to opposite divided by adjacent. So if I divide 6 divided by 4, I got 3 over 2, or like 1.5. And I look at the final step. So what I've just found out there is that the tan of the angle I'm looking for is 3 over 2. To find out what the actual value is, I'm going to use that inverse tan. That's where you're going to do it reverse, to find out what's the angle that will give you this as the tan. So I'm going to press the shift or second function, and then I'm going to look for tan on my calculator, which is here. And if you see the little in yellow, it's tan to the minus 1. That's the inverse of tan. So I'm going to press that, tan into minus 1. Now I just put in brackets the value I want to find it. We know it's 3 over 2. 3 over 2, make sure the brackets are around it. That's going to give me an answer. That answer is 56.3099 degrees, because I've got my units in degrees. If it was radians, it'll be closer to 1 radian. For these calculations, make sure your calculator is in degrees. There'll be a little d up the top, right? And it'll vary depending on your calculator, but send me a photo of yours if you can't convert. So we know how to do that, all right? Or hopefully we do. We can, given 2 vectors, we can move them so one is ends where the other one begins. Make the triangle, find the resultant, okay? And that's just another way. Another way of doing that is like, let's say those are the two again, like we started with. We know that the resultant's going to be like that. Remember the parallelogram law? It's the same thing. It's just a slight twinge in the variation of the parallelogram law. And that's all well and good for 2, okay? We can now, with a little bit of maths, and it's not always easy, but we can find out the resultant of 2 vectors, whether we're talking about acceleration, speed, force, whatever. What about if there's 3? Now, the thing is, on the Leave Insert course, the only time we're going to have to deal with three vectors is if two of them are at 90 degrees to each other. Let me explain what I mean. Let's say you've got a situation where I've got three vectors. I'll draw them in again. These two are going to be at 90 degrees to each other like that. And the other one will probably, let's say it's coming off like that. So first, I'm going to be a little bit neater on this because it's going to be a bit confusing. I'm going to call this vector 1, 2, and 3. So what you're going to do, if you're trying to find out the resultant of all this, so let's put some numbers on it. Let's do an actual example. Let's say it's very tempting to go with force, and I will. Let's go with force. Let's say that this is 30 newtons, something's pulling 30 newtons that way. Let's say going up, it's 20 newtons. And because this arrow is pretty much the same size, no, let's make it a bit bigger. Because remember, the arrow indicates the, let's go 20, whatever. So 20 newtons again. Okay, and the reason I said 20 there is because I'm trying to manipulate things in a certain way, which at the Leave Insert will be done for you. If I made this, let's say 100 newtons, right? The resultant of these is going to be off like that somewhere. But in the Leave Insert, they're actually going to be nicer than that. And usually, the resultant is going to be up like that at 45. So it's going to be easy to do this last step, which I'm going to say now. So first off, let's find out the resultant force of these two. Okay, well, it's going to be the diagonal of a parallelogram created by these two fellas here. Or, like we said earlier, you could move this vector over like that, and the resultant is the one that joins them. So these are just two variations of the same thing. So we're looking for this line here. Okay, so let's use Pythagoras' theorem. So it's going to be 20 squared plus 20 squared. I'll leave it units just for the sake of speed, but don't forget they're always there. So it's 20 newtons squared plus 20 newtons squared. So we have 20 squared equals, because of two of them, because 800 square root of 800. So my answer is 20 root 2 newtons. And remember, just like I said before, that's an actual number. Just press SD and it will tell you that is 28.28. Let's put it up here for a minute. 20.28 newtons, which makes sense because it's the longer of the diagonals of the hypotenuse. Okay, so what we just found out is that the resultant force of these two is going to be in this direction with 28.28 newtons. Now, many of you have probably already figured out that this is going to be 45 degrees because these are both equal. But let's just verify it. Let's not presume that. Let's use our trigonometric ratios to make sure. So let's go back to what we know. We'll ignore the one we found out for a moment. We know the adjacent. We know the opposite. So again, going back to here, I think tan is going to be our friend here. So opposite over adjacent. So tan of this angle that it makes here is going to be opposite, which was 20, over adjacent, which is 20, newtons over newtons, which is just tan of 1. So let's see what the inverse tan of 1 is. Oh, I pressed sign. I was wondering how I got 0.01. Sorry guys, you just saw my word flash beside before my eyes. Tan of 1, let's the right button this time, is 45 degrees. What a surprise. Okay, so we don't even need to know that. Well, we do. So at 45 degrees. So this resultant is going up 45 degrees to horizontal with 28.28 newtons. Now, this one is pulling in directly opposite it at 30. So to find out the overall resultant force, remember that if two vectors are going against each other, you just subtract them, and that's the difference. So the overall effect here is going to be this 30 is trying to pull it this way, but we're trying to pull it up by 28.28. So our final answer is just 30 minus 28.28 will give us 1.72 newtons in that direction. That's the resultant force. Now I know that sounds very, very complicated. Let's go through it one more time. In Leave Insert, whenever you're given three vectors to kind of figure out, two of them will always be at right angles. Do that one first and figure out the resultant of that right angle one, and then compare it with a third. Okay? We might try one more example. And again, these are just made up examples. We'll have a go with some of the textbook questions in the live one. So, and again, just kind of completely making this up. So let's go with meters per second as our next vector. Could use any vector, but let's go with that. Let's say that that's 10 meters per second. 10 meters per second. Let's say there's a third one going up like that. Let's say that's at 45. Remember, at leave insert, they're always going to be like that. Let's say that's at 15. Why not? Meters per second. Okay, so we're trying to find out what's the overall result of all three of these vectors. And let's just think, before we do the calculation, let's think it through. This vector is trying to pull it over in that direction. These two, because they're both accelerate, they're moving out like that, they're going to bring it in this direction as well. So it should be going in that direction at a large amount. So let's figure out what it is. Well, first off, let's use the parallelogram law or the triangle law, whichever floats your boat, to find out, ignore this vector, and let's just get the resultant of these two. So if you've got 10 and 10, the resultant's going to be going up like that. And it's going to be the square root of 10 plus the square of 10 will be the square root of this, just using Pythagoras. So that's 100 plus 100 is 200. Oops. So I'm just going to say square root of 200 is 10 times root 2. So the resultant of these two is 10 times root 2, and it's going to be at 45 degrees, because remember, we're going to use tan, which was opposite over adjacent, which is 10 over 10, so that's just 1. So just to verify again for ourselves, we're going to say shift tan 1 is 45 degrees. So we know that the resultant of these two is pulling in the same direction as this third vector, but with a magnitude of 10 by root 2 meters per second. And remember, that's just a number. Just because it's inserted, don't get intimidated. So overall, the overall effect of these three vectors are the resultant of these two added to this fella here, because they're all going in the same direction. So it's just 10 times root 2 plus 15. So, and see, even there with my calculation, for the final answer I've got 15 plus 10 root 2 meters per second. Now, again, that's just because the calculator is trying to preserve accuracy as long as possible. But if I make it give me a numerical answer by pressing an SD button, I get 29.142 meters per second is my final answer. Okay, it's a lot to take in, so make sure that makes sense to you first. So to reiterate, do the resultant of the two that are 90 degrees and then factor in the third one, which is either going to be directly with that one or against, depending. Okay, I'm going to give you a small break here for a second.